So we are very glad to have Deeparnab kick off the Monotonicity Festival. So Deeparnab is an associate professor at Dartmouth College, associate professor of computer science at Dartmouth College. Prior to this, he was at Microsoft Research Bangalore. He's interested in combinatorial optimization, sublinear algorithms, and he has done fantastic work in these areas. Perhaps it's inappropriate of me to say, but Deeparnab was an IIT Bombay alumnus. Feels wrong to say this because he was here way before my time. But yeah, we are very glad that you are here, Deeparnab, and so please take it away.
Thank you, Akash. So thank you everyone for joining. So it's first of all, I appreciate that it's 5:30 in India and it's early here. So arranging this timing was something of an inconvenience to all of you. So I apologize for that. But thank you for coming to listen to this series of lectures on monotonicity testing. Maybe my only regret is that I could not come and give the talk in person. It's always a joy to come back to IIT Bombay. Okay, so this series of lectures is about monotonicity testing. This is something that I've been thinking about and working on for maybe over 12 years. So I wanted to, so this particular lecture is going to be a sort of gentle introduction, and it's going to be extremely informal. So anytime you have a question, anytime I say something that you don't understand, you should just abruptly interrupt, just start speaking. I won't be monitoring the chats and everything. It's something that I'm not very good at anyway. But Akash, if you do see some chat, then you should just stop. Okay, thank you very much. Good. So let's sort of start with the so what are monotone functions? So before I go into monotone functions, we're going to talk about algorithms, and the input of this algorithm is going to be a function, and the thing that we will assume is that this function is given to us like a black box. So it gives some input x and outputs an output f of x. The domain of this function, when we talk about monotone functions, the domain is assumed to be some partial order, okay, some big partial order. And the range is supposed to be some total order. Let's just assume reals for now. So once we have that, then we can define what a monotone function is. So a function is monotone if for any two inputs in the partial order such that x and y, such that x is less than y in that order, we should have fx is at most f of y. The output of the function value should be in the total order respects this partial order. If x and y are not comparable, which can happen if since it's a partial order, then fx and fy can be, there is no restriction on that. So that at a very high level is what a monotone function over a general partial order is. The series of talks is not going to talk about general partial orders. I am going to talk for a few minutes, maybe the next 15 minutes, about a general partial order. But most of the whole lecture series will be about two partial orders. The first one is going to be the hypercube. Okay, so the partial order is Boolean vectors, 0, 1 vectors with d dimensions. And furthermore, we're going to talk about the range also will be Boolean. So the range is also going to be 0, 1. And here, so the monotonicity is sort of, you can think about it, there is a input is d dimensions and each input bit is 0 or 1. And a function is monotone if flipping an input bit, any input bit from 0 to 1 cannot make the function go from function value go from 1 to 0. So that's what a Boolean function is. So a Boolean function over a hypercube is just it's a function defined over this domain of size 2 to the d, and each range is 0, 1. So we're going to talk about Boolean functions over hypercubes more later in the talk. But the other partial order that we'll be talking about is a generalization of this hypercube. It will be the hypergrid, where again the input has d coordinates, but now each coordinate can take a value from 1 to n. Okay, 1, 2, 3, 4 up to n. So integers from 1 to n. So this is the domain is the hypergrid. So it's denoted as this n to the d. We are still going to be talking about Boolean range. So the function is still 0, 1. And now the way to think about it is that increasing any input coordinate cannot flip the function from 1 to 0. So that's what a monotone function is. Of course, one can talk about general ranges, and there is a lot of work on that, but to chart out the territory that we are going to talk about, we're going to talk about only Boolean range functions for most of the lecture series. Okay, so that's monotone functions. We need to define the problem we're going to talk about. We need another concept, which is called the distance to monotonicity. Okay. So distance, before we talk about distance to monotonicity or distance to a property, let's fix what we mean by distance between two functions. So given any two functions f and g defined over a domain, we're going to define the distance between these two functions is the fraction of the domain points where f and g differ. Okay. Again, this is a very general definition where the range can be arbitrary and the domain can be an arbitrary partial order or arbitrary domain. And we are looking basically at a Hamming distance between f and g in a fractional sense. We are not looking at how much they differ by. So that's something, as in one can ask whether those notions of distance matter. But for this series of talks and in general in this area, the distance between two functions is often called as the fractional Hamming distance. You can think of it as a fractional Hamming distance. So that's distance between two functions. Now, with this notion of distance, we can define the distance to any property, but in particular for the property of monotonicity, we define the distance between f and a monotonicity is I go over all monotone functions, and I look at the closest function to f in this notion of distance, and I output that distance. So that is defined as a distance to monotonicity. So it's min over all monotone functions g, distance between f and g. So clearly, if f is monotone, g equal to f will imply that the distance of a monotone function to monotonicity is 0. Okay, so this number, this parameter, is some parameter between 0 and 1. Okay, so we've defined monotone functions, we've defined distance to monotonicity. Now we can tell what the problem of monotonicity testing is. So the input to this problem is a black box access to this function over some domain to range. We'll be mostly talking about Boolean hypercube and Boolean range, but more generally, this is the input. Furthermore, we assume that there is a distance parameter epsilon given as input. This parameter, think of it as 1/10, okay, concretely. What is the goal? Or a monotonicity tester is a randomized algorithm, and it has the following properties. If f is monotone, if the distance to monotonicity is 0, then this tester must say yes with probability at least 2/3. If the distance to monotonicity is bigger than this distance parameter epsilon, which is part of the input, then it must say no with probability at least 2/3. But if the true distance is somewhere between 0 and epsilon, then it is allowed to do whatever it wants. Okay, so it's sort of a promise problem, or rather its output is only guaranteed under the promise if it's either monotone or if it's far from monotone. So this notion of in this series, if you hear far from monotone, we are basically in this world. We are saying the function is at least epsilon far from any monotone function. I need to change the function in at least epsilon fraction of the points to make it monotone. So that's this section. And in that case, when the function is really far from monotone, the algorithm should catch it, should say no with probability at least 2/3. And if it is monotone, then it should say yes with probability at least 2. So that's the problems. Any questions so far? Okay. So let me say two sort of things that we will often talk about. So these are again terms that you will hear across the 3 weeks. Sometimes we want that if the function is monotone, you must say yes with probability 1. Okay, so there is no error. If the function is monotone, you cannot say no. We don't allow any error like that. So this kind of an error is one-sided. I make an error only when the function is far from monotone. And oftentimes such testers which have only one-sided error is called a one-sided tester. Okay, so that's a term that you'll hear. So a one-sided monotonicity tester is which always accepts a monotone function. The second thing you will hear is the following. So this randomized algorithm is a query algorithm. It queries a function, sees an answer, and then makes a query and then sees an answer. So it could do this in various rounds. A tester is called non-adaptive if all the queries is made in one round. So in particular, the queries that the algorithm makes don't depend on the answers to previous queries. So the algorithm can be thought of as it's a randomized algorithm. So it tosses some coins and it figures out a bunch of domain points and feeds it to the black box. The black box then feeds out all the answers. It looks at the answers, does some computation and says yes or no. So this is such an algorithm is called a non-adaptive algorithm, as opposed to an adaptive algorithm, which could ask a question, see the answer, do some computation, then ask another question, see the answer, and so on. So today, and most of the talks in the whole six lectures are there, we'll be talking about non-adaptive one-sided testers. So that's going to be the focus. And of course, when we talk about open directions, we will be talking about adaptive things maybe. So the big question here in general in monotonicity testing is, as a function of the domain size, range size, and this distance parameter epsilon, what is the query complexity of this task? And in particular, you can talk about non-adaptive one-sided testers. So that's the general question of monotonicity testing. So hopefully the question and the setting is clear. So with that in mind, let me sort of tell a little bit about the objective of this series. So we want to sort of give a survey of monotonicity testing, but mostly with a focus on Boolean functions on this Boolean hypercube and Boolean hypergrid domain. And the reason is that there is a lot of richness that has been uncovered over the past, it's been around 25 years now since this problem has been studied. And in particular, there are connections with discrete isoperimetric problems that arise in geometry. So that's the kind of connection that we also want to talk about over the next 3 weeks. And then sort of also end with some open directions and open questions, which are, there are some questions that are vastly open and one we will meet very soon. And there are some also loose ends to tie out in this study that we have in the last 25 years that we've seen. So that's the overall objective of these 6 lectures. And today, what I'm going to talk about, I'm going to start off by actually talking about the most general problem, and I'll give you the state of the art. Okay, so it's not, so it's sort of, there's not much has happened in the general problem. And so I want to sort of start off with that. And then I'm going to pivot to this Boolean functions of the hypercube domain. So I'm going to talk, so my talks will be mostly restricted to the hypercube today and on Thursday. Hadley will talk about hypergrids, and then Sesh will also talk about both cubes and grids. So I want to talk about that. I want to tell you the original tester that was proposed 25 years ago or around 24 years ago. And already that tester has some connections with this geometry. I want to sort of introduce that. And if time remains, I want to introduce this the tester that actually is optimal in some sense, and perhaps give an indication of more isoperimetric results, and we'll carry over on Thursday. So that's sort of the plan. Okay, so let's talk about general monotonicity testing. So so if you think about, again, monotone functions, well, the definition is sort of maybe simple, like if x is less than y in the partial order, fx is less than f of y, that's pretty simple. But what is sort of a little bit hard to grasp is this notion of distance to monotonicity. Because if you think about it, I give you an arbitrary function. I'm taking a min over all monotone functions, and there are lots of monotone functions. So this distance is something that one needs to get a handle on in order to understand before even one can understand how to design algorithms. And this is not just for monotonicity, this is true for any property. And for monotonicity in particular, there is a very nice handle on our distance, and that's what I want to begin talking about. So there are 2 ways one can think about a handle on the distance. First way I think is constructive. So So the way I think about it is, I want to figure out what the distance of f to monotonicity is. So let me actually look at f and try to fix it, try to make it monotone. Okay? So give more details. I want to look at f, and suppose I can make some number of changes like s and make it monotone. Well, clearly this means that the distance between f to monotonicity is at most the distance between f and g. So that is at most whatever number of changes I made constructively divided by the domain size. So this is just a sort of almost a trivial statement. But how is it used? And we will see a use of it in 20 minutes or so. Is that you look at f and you try to make these changes to make it monotone. We are trying to understand how to capture, how to say no when the distance is large. Well, if we need at least s changes to make f monotone in our constructive method, then we will try to look at these changes and try to capture a violation. So that's one way and again, this is very abstract. It's not very clear. It will become clearer as we go, but that's one way one can get a handle on the distance, like constructively fix f to a monotone function that gives an upper bound on the distance. Is that clear? Sort of. Again, you should just stop me if there are any questions.
I'm familiar with the literature. I do not know if other people are like able to unmute themselves. Do you know?
Oh, when you say do you know, do I know is the
I am. You can hear me, right?
Yeah, I could hear somebody. Okay, great. Thank you.
Yeah, I have no question.
Okay, so that's one way. But the other way is the following. And this is, let me spend a little time on this. The other way looks at the following graph. So again, I have a partial order. So my graph has a vertex for every point in the partial order. And I draw an edge between x and y if it's a violation. So x is less than y in the partial order, but fx is bigger than f of y. So that's a violation graph. So given f, I have a violation graph. So this g should be parameterized by f. And now here is the non-trivial observation, is that the distance of f to monotonicity is precisely the size of the vertex cover of this violation graph divided by the whole domain size. So that when I say fractional, I meant divided by the domain size, not a fractional vertex cover. Okay, so distance to monotonicity, we are saying is precisely some object. What is that object? It's a minimum size vertex cover divided by the size of the domain. What is a vertex cover? A vertex cover is a subset of these vertices which hits every edges. So it's a subset of vertices so that every edge has at least one endpoint in this vertex cover. So in particular, in this example, if I look at just this graph on 4 vertices and 4 edges, this pink vertices are one vertex cover. Every edge has at least one endpoint, which is pink. And the claim is that if I look at the smallest vertex cover, that is precisely the distance to monotonicity. So in particular, and I'll not spend too much time on it, the main reason why this is true is that if you give me any vertex cover, for example, in this picture, this vertex cover, then I can find a function g which changes the function only on these pink points and makes it monotone. And the way it goes, it looks at the smallest pink vertex, smallest in the partial order sense. And like in this case, this is the smallest one. I hope you can see my arrow. So this 3 is compared with 2, 1, and 0. So to make it, these edges vanish, so all the violations go away, I should make it the smallest among 1, 2, and 0. So I make it 0, and I sort of repeat this process recursively. And then this gets fixed to 1, and this function becomes monotone. So again, this is first of all, it's fast if you've never seen this. But the takeaway is that if you give me this object, this vertex cover, then that I can change the function on precisely those points and make the non-monotone function monotone. So that gives me the handle on the distance. And this is not a trivial fact that I can fix like this and I can make it monotone, because what is not clear is a change. Why doesn't it introduce more violations? So that's a thing that requires some thought, but it can be proved. And the reason I'm stressing, talking a little bit more on this is for other properties, some other properties, and I don't know if we'll get to, in the open problems, maybe we'll get to that. For some other properties, such a handle is actually not present. In particular, for a property like submodularity, we don't know of such a handle, which leads to our lack of understanding of testers. But coming back to monotonicity, so the takeaway is, if I look at this big violation graph, the distance to monotonicity is precisely the size of the vertex cover.
So Deeparnab,
yes,
is it because all the other edges, they go to the vertex covered vertices, and otherwise you don't have edges. So these partial relations don't matter. Is that the
So
reason?
good. So what is sort of simpler to see is that if I fix the vertex cover, these edges vanish. I'll fix all these edges. They'll not be violations anymore. What is a little bit thought that is required is it does not introduce new edges. So if when I fix this this point from 3 to 0, I don't bring out another violation. So there is no so for example, it is not the case that there was another point here, which I am hopefully can see where my arrow is, which was a which was not a violation, and the 0 made it a violation, or a point here. Does that make sense? I don't know.
Yeah, thanks.
Okay. Good. So again, so to summarize, the distance to monotonicity is the vertex cover. But the vertex cover also is not a nice object in a general graph. It's an NP-hard object. So
Deeparnab, just to be sure,
yes, Jacob.
the edges that you call violation are not necessarily the edges of the Hasse diagram of the poset, right? They are
They are not
they are
exactly.
They're
Yeah. So
pairs of comparable elements.
Absolutely. So the edges, this edge here I'm drawing, it's not, as Jekmar says, the Hasse diagram, which is the smallest description of the partial order. It is just all the possible pairs which are violating. Good. Good. So distance is equal to vertex cover. But vertex cover is also an early object. So what one looks at is actually matchings. So here is the fact that any maximal matching has size at least half of the minimum vertex cover. So what one can conclude, and this is the part that is important takeaway, that if a function is far from monotone, if the distance to monotonicity is at least epsilon, then there is a vertex cover of size epsilon times the size of the domain, which means that there is a matching in this violation graph of size at least epsilon times the domain size by 2. Okay. What is a matching? A matching is a collection of disjoint pairs, disjoint comparable pairs as drawn here, where each of them are a violation to monotonicity. So these are various certificates. So if you catch any one of these in your queries, then you know that the function is not monotone. And what this fact is saying, that if the distance is large, then such a big matching, such a big pair of, a big collection of disjoint pairs of violations exist. So if epsilon is 10%, there is a size of 5% times the size of this domain. And this alone implies a very simple tester. Okay. So this is a theorem from Fisher et al. From Stock 2002, which basically says that for any partial order of size capital N, so size of D is let's say capital N, then I can get away by making only square root n many queries. Okay, so there is and the dependence on epsilon is also shown in the theorem. So there is basically roughly square root n capital N queries you can make and test monotonicity. And the algorithm is trivial. You basically sample points at this rate. So every point you pick at rate roughly 1 by square root the size. Okay, so if you sample points at this rate, you're going to and query them. So if the number of points you'll query will be roughly 1 by square root d times d, which is roughly this size. You check for violations among comparable pairs in these. If you find one, you say no. If you don't find one, you just say yes. Clearly, if the function is monotone, you will not say no, because you'll say no only when you find a violation, which is a certificate of non-monotonicity. So it's a one-sided tester. It's non-adaptive. What we need to worry about or argue about, if the function is indeed far from monotone, why is it that this thing will catch it? And the reason is the following. It's simple. So you look at any such and so there's a large disjoint collection of violating pairs sitting here. What's the probability that you pick this point and this point both in your sample? It's roughly p square, where p is the size of this. It's like 1 by square root d. And so the probability that you don't pick it is 1 minus p square. And the probability that you don't pick it for all of these so many violating pairs is roughly 1 minus p square raised to the size of, m, and they're independent because they're all disjoint. And then if you do a little bit of, analysis, you'll get that this number is at most 1/3. And the reason is that p square and the size of m, which is basically roughly the size of the domain, cancel out. And so when p is 1 by root d, p square m cancels out. And that's a similar reason why, birthday paradox, where if you have, if you square root the number of days in the year, many people, you get a collision. So that's the similar kind of reason. So that's it. So this is the, yeah, Jayakumar?
Just to be sure, you will sample these points, but nevertheless compare every pair of comparable elements here within that.
Yes, good.
that
So
the
when
num-
so the query complexity is square root d, but I'll compare and it'll take me maybe d time too, but that's just time. Is
Got
that?
Yeah, got it.
Okay.
Yeah.
Yes. So we don't know a priori who are comparable and who are not. So we're going to compare every pair.
So just to repeat, Deeparnab, you're saying that
Yeah.
the number of queries is square root d. The time
Yeah.
taken can be way larger, but I don't care about the time taken, at least right now.
For this one, yeah, for this one, I don't. Yeah, right now. So, right. Good. Other questions for this? This is like the, sort of a very simple and in some sense, an exercise that can be given in a randomized algorithms class. It's a nice exercise if you're teaching this. And maybe the thing is that, okay, so this is a result in Fisher et al. What Fisher et al. Also proved, and this is it's a very beautiful and non-trivial result, is that they proved so this is again for general posets and general range, and they proved that you cannot have really super good testers. Okay, so this is a mouthful, but it basically says you cannot have a tester which is non-adaptive and makes only logarithmic or polylogarithmic in size of the domain. So the domain, so the trivial thing is I query everything, so that is size domain. This one says you can do square root domain. And this one says you cannot do much better in general. You cannot go to a logarithmic in the domain or even polylogarithmic in the domain. But cube root of the domain, fourth root of the domain are still open. And this is for non-adaptive. So this was a beautiful result, and it sort of connects Ruja's and construction of certain classes of Ruja-Zamirati graphs to this testers. I'm not going to talk about it, but if people are interested.
So, this is non-adaptive, one-sided?
No, I think it's two-sided.
Oh, okay.
So, sorry, Deeparnab, actually, so
Yeah,
can
sure.
you in these two terms once, like what is this adaptive and non-adaptive tester?
Yeah, so a non-adaptive tester makes all its queries. So it's basically, it is a randomized algorithm, which is using randomness to figure out, I'm going to make these many queries, and then feeds it to the black box, and the black box gives you the answers. You churn these answers and you say yes or no. An adaptive algorithm could look like, say, binary search. You make a query, you look at the answer, and then you say, I'll make this query next, and then so on and so forth. So that's an adaptive algorithm. So adaptive algorithms can have much more power than non-adaptive algorithms. And this theorem here is ruling out non-adaptive algorithms of a certain query complexity.
So adaptive means by default, it is not one-sided, right?
No, it could still be one-sided. So adaptivity is only a way how the algorithm is interacting with this function, with this black box. One-sided means if the function was monotone, then all the things after any computation you do, you must accept. There is no chance of making a failure if the function is monotone. Two-sided means even if the function was monotone, I could say no with some, say, 1/3 probability.
Okay.
These are two sort of different axes of comparisons. Does it make it clear?
Yeah, thanks.
Good.
Just to compare the upper bound and the lower bound. So the upper bound sort of is like 2 to the half log d. Is that how I should read it? Yeah.
Yes.
So
it's 2 to the
so
half log d.
And I mean, to improve those results, we would probably want to make that half to be like 0.5, 0.3, 0.2, 0.1. But the point is that, and the lower bound seems to say that you cannot move the exponent up. Yeah, the C is on top of the log. So there definitely the constant is 1.
Correct.
The best you can hope is
Absolutely.
kind of fiddle around with something smaller.
Yeah, you can get square root d, cube root d, fourth root of d, and so on.
Okay,
But you
yeah,
cannot
got
get 2 to the square root log d. In fact, this is 2 to the log d by log d also you cannot get, but
okay, got
very
it.
good. But this is non-adaptive. So in particular, I'll make 3 more remarks before going to Boolean functions. First is that this theorem, the upper bound is for any domain and any range, but the lower bound also holds for Boolean functions. So even if the function is 0, 1, the same lower bound holds. And in fact, they have this paper has a reduction that you can somehow assume that the poset is bipartite. So there are it's a bipartite directed poset. So even there you have the same lower bound. But more importantly, it does not rule out polylogarithmic adaptive testers. So the only thing about adaptive testers, what you can find, so there's a general fact, if there is a Q, if there's a lower bound of L on non-adaptive testers, then there's a lower bound of log L on adaptive testers, because any adaptive tester of query complexity Q can be moved to a 2 to the order Q query complexity non-adaptive tester. So that's the only thing that is ruled out. So tomorrow there could be a log D sized adaptive tester, which is not ruled out. And that's it. This is the state of the art. So there is no, for a general poset, this gap has remained for over 22 years. So if there's someone is wishing for a problem to sort of sink their teeth into, this is one, which is there's a big gap. Good. So I am now going to talk about, I think none of us are going to talk more about general posets anymore, unless at the very end, Sesh brings it back up an open problems deck. But that thing is really open. We don't have really good ideas. But a lot has happened in structured domains, in particular this hypercube and hypergrid. So that's sort of what we're going to talk next. So again, before I move on, any questions about the problem and the general poset setting? So now, let's sort of align ourselves. So let's forget our posets and everything. So now we have a Boolean hypercube. So there's a 0, 1 to the D. And I have a function which assigns every point in this cube to either 0 or 1. I want you to also think of the same, this sort of function also as a set system. Okay? In particular, every point that the function gives the number 1 is present in my set system. And so the points of the subset of the hypercube where the function evaluates to 1 is some region, some set system, which is I'm showing as a green blob here. Okay? And a monotone function corresponds to the sort of downward closed set system. So if a point is in the set system, then its subsets are also in the set system. So it's a picture like this. And a far from monotone function, which means that I have to change the function in at least epsilon points to make it monotone, which means I have to take the set system and I have to sort of either add sets or delete sets, and a lot of them, like epsilon times 2 to the D of them, have to sort of move around to make it monotone. So the far from monotone functions is some sort of a jaggedy ball like this. So it's a good, so I'm saying this because we're going to talk about isoperimetry theorems in very soon, but that's the two sort of dual views that one should have. So monotone Boolean function should be considered as these blobs in this hypercube. Okay, again, the function is monotone if making a 1 to a 0, a 0 to a 1 cannot make the function value a 1 to 0. So let me tell a little bit, and I'll go a little quicker here about the history. So this problem was studied in a paper which is Fox 1998 by Goldreich, Goldwasser, Liman, and Ron, called monotonicity testing, and they gave a D by epsilon query one-sided non-adaptive tester. Now let's just compare ourselves with the upper bound that we had in general. Okay, so the size of the domain now is 2 to the D. So square root of 2 to the D is 2 to the D by 2. while this number here is logarithmic. Again, think of epsilon as a constant like 0.1. So this number is like logarithmic in the size of the domain. Okay. So already this is saying that if you have structure, which the Hypercube has a lot of structure, then you can actually get much better query testers. Okay, so this was the result. It was and we're going to talk about. I'm going to tell you this whole tester and its analysis in the next whatever 25 minutes that I have. The same paper, the Fisher et al. That we talked about in a bit, also showed that for this Hypercube domain, if you are looking at one-sided non-adaptive testers, the dependence on the dimension of the Hypercube D, well, it cannot be better than square root of T. Okay. And this was the state of the art for a while, till a paper of mine with Sesh around again 10 to 11 years ago, we sort of gave sublinear in dimension. So we gave D to the 7/8. So we went below D, query one-sided tester. And this was after that, there was a flurry of work. So this was very soon improved by Chen, Servideo, and Tan. But the more important thing, and we'll maybe in our work, was connecting this this sort of problem of distance to monotonicity of Boolean functions to isoperimetric theorems. And once that was done, there was this seminal work, and I'm going to talk more about in the next lecture, of Koht, Minzer, and Safra, which basically nailed the bound. So it basically gave a square root D by epsilon square one-sided non-adaptive tester. They also showed that the dependence on epsilon is also cannot be much better than this. So it's if you're thinking about one-sided non-adaptive testers, that is the end of the story. And then if you look at even two-sided testers, what Chen, Weingarten, and Xi showed is that the dependence on D is still square root D. So being wrong, a little wrong when in the yes case also doesn't buy you much. So that's sort of the state of the art. And I'm going to talk about the first thing today and the next thing later on Thursday. That's the plan for my lectures. But before I move on to the first edge, the D by epsilon tester, one thing you will see is that everything here is non-adaptive. And the question is, what is known about adaptive? And that's actually one of the open questions here. So it is known that adaptivity, there is a lower bound known, but the lower bound is not square root D, but cube root D. And there is this gap between cube root D and square root D for this problem, which is one of the things I think will be very interesting to solve for Boolean monotonicity testing over the Hypercube. I'll repeat this open problem maybe at the end of the Thursday's lecture, but all this slide is for non-adaptive. Okay, so that's a history. You'll probably let's get to this very nice tester called the edge tester. Okay, so again, problem is I have this function defined on this Boolean Hypercube. It's a Boolean function, and I want to, if it is monotone, I want to say yes all the time. If it's not monotone, I want to say no. And the tester is the simplest tester you can think of. You can think of the Hypercube as this graph, right? Which so you sample an edge of this graph. So you sample X and Y uniformly, edge uniformly at random. So you sample an X, you take one of the coordinates, which is 0, you make it 1, you get Y. You query the function value at these two endpoints. And if you get a violation, if fx is 1, the smaller point is evaluates to 1 and the upper point evaluates to 0, you reject. Otherwise, you accept. Okay. So that's not quite true. So this is, so what the theorem is going to be is that so first of all, if my function is monotone, then I will never find such an XY pair. But the main theorem says if the function is far from being monotone, if the distance to monotonicity is at least epsilon, then the above tester rejects with probability epsilon over D. So again, thinking of epsilon as a constant, I will catch a violation with probability 1 over D. So the final tester actually repeats this process roughly D by epsilon times. And anytime if I find a violation, I reject, otherwise I accept. So then a simple calculation shows that will actually reject a function which is far from monotone with at least constant probability. So this is the heart of this theorem is the heart of the testing. So the statement of the theorem clear? If the function is far from monotone, then a random edge of this Hypercube will catch this violation with probability epsilon over D. And maybe this is a nice time to talk about or to sort of what Giacomo had pointed out. So the hypercube itself is a partial order domain where the edges that I've drawn here for this sort of 4-dimensional cube is the Hasse diagram. Okay. And what this edge tester is saying is you sample an edge of the Hasse diagram and check for monotonicity violation. We are not, this graph is not the violation graph. A violation graph, if this was 1 and this was 0, then there would have been an edge between these 2 points also, but they are not there. So this edge here is the edge of the hypercube. This I wanted to again stress. Okay, so this is the theorem. And the theorem basically is saying that if a function is far from monotone, then there are lots of violating edges on the hypercube. In particular, it is saying that if the distance is far from monotone, then the number of violating edges is roughly epsilon times 2 to the d. This implies the previous one because the number of edges in the hypercube, the total number of edges is roughly d times 2 to the d. It's d by 2 times 2 to the d if you want. And so if the number of violating edges was epsilon times 2 to the d, the random edge, the probability it catches it is going to be this divided by d times 2 to the d, which is epsilon by 2 to the epsilon by d. So this is the theorem that I want to show. Before I show the proof, let me sort of give a geometric interpretation of this theorem, right? So again, I want you to think of this hypercube as a directed graph where I am directing the edges of the hypercube from lower Hamming weight endpoints to higher Hamming weight endpoints. And I want you to think of this function as a subset of this hypercube, this jaggedy green subset. And what this is saying is that all the edges that, if I look at the directed outcut of this hypercube, all the edges that start inside and point outside, which are precisely the violating edges because the lower endpoint is 1 and the upper endpoint is 0. That size, that edge boundary, normalized by the size of the hypercube 2 to the d. This is called the normalized out boundary of this set A. So A is the set where the function value takes 1. If I look at phi plus A is the directed out boundary. So what this theorem above is saying is that if function is epsilon far from monotone, or if the set is epsilon far from monotone, then the directed out boundary is omega epsilon. So this omega epsilon is normalizing, takes this care of this 2 to the d. Why am I saying this? Because instead of the directed, if you look at the undirected world, where again I have a subset of ones, and now instead of looking at only the violating edges, I look at all sensitive or influential edges, all edges which have one endpoint 1 and one endpoint 0. And this includes edges which go from 0 to 1. So that's the set of, clearly it's a superset of these edges. Well, it is very well known that this subset of influential edges, which is the subset, if I define phi of A without the plus to be the size of these edges divided by 2 to the d, then this is comparable to what is called the variance of A. The variance of A is basically a notion of the size of A, which is the number of ones times the number of zeros. If you think of if you sample a point and you look at f of x and you take the variance of that, that's what the variance of the set is. And it's a sort of a folklore theorem. It's called the Poincare inequality because it's a simple case of a much more general thing, is that this size, this edge boundary is always at least the size of the set. It's some sort of an expansion theorem. So this has been known, and what I'd like to impress upon you is that this theorem that Goldreich et al. Proved is an expansion for directed graphs in some sense. In the undirected world, it says if I have a large enough or a balanced set, which is of a certain balance, then there are lots of edges coming out of it, both directions. Instead of the variance, if I had distance to monotonicity, then this GGLRS says that I still have lots of violating edges coming out of it. So this is sort of I'm just connecting them, and it's at a syntactic level right now. But before I move on to actually proving this, I want to make sure that this sort of mirror is the definitions are sort of clear. So any questions about what these phi plus and phi A mean? Okay. So I'm going to now, I guess, so we're going to now talk about the proof of this in the next 15 minutes that I have. So this is the statement that I want to show. So if a function is epsilon far from being monotone, then the number of violated hypercube edges is at least epsilon times 2 to the d minus 1. In fact, the constant is given. And this proof is from this paper, this combinatorica paper of Goldwine, Goldwasser, Lehman, Ron, and Samartinsky. And the proof is going to be via this fixing argument that I had alluded to earlier. I'm going to start, so the way it goes is, I'm going to start with my function f, and I'm going to describe a procedure which will first, construct a function f1, then f2, and then so on up to fd. And the property will be the following. When I go to from f to f1, across a dimension 1, so I name the dimensions 1 to d, f1 will have no violations across that dimension. So I'll fix all the violations across that dimension. And then when I go from f1 to f2, f2 will have no violations across dimension 2 and no violations across dimension 1. And so on and so forth. fi will have no violations from 1 to I. And when I reach fd, fd will have no violations across any of the dimensions, which means that fd is going to be a monotone function. That's the process that we'll describe. And there will be the following important property will be there, that when I go from fi to fi plus 1, I'll make some changes. But the number of changes will be no more than the number of violated edges in f across that dimension times 2. So this is when I'm going from fi to fi plus 1, the number of changes I make will be bounded, will be charged to the violating edges across this dimension in the original function f. Now, if I were able to do this, then the total number of changes I make when I go from f to fd, this should be d, while it's just the sum of all these changes I make, it's 2 times the number of violated edges in the hypercube altogether in f. So that's what I get. And the number of changes I make is a distance between f and ft times 2 to the d. But the distance, if it is bigger than epsilon, I get epsilon times 2 to the d is at most 2 times the number of violated edges, which implies this theorem above here. The number of violated edges must be at least epsilon times 2 to the d minus 1. Okay. So the whole game is to go from one function f1 to f1, f1 to f2, f2 to f3, so that I am making changes, fixing the function dimension by dimension, and charging my changes to the number of to the violated edges in f across that dimension. Okay. So so the argument is called a switching argument. It's a very nice argument. So let me just tell you what the switching is from f to f1. Okay, so I fix the dimension 1. So think of this line. So all the points below are all the points which are first coordinate 0. All the points above are the ones which are first coordinate 1. And these yellow edges are precisely the edges which violate monotonicity across this dimension. So it has 1 where it should have been 0, and it has 0 where it should have been 1. So the switching argument looks at all, so again, it's all analytic, right? It's not algorithmic. So you're looking at all these edges, so they form a matching, and you fix them just by switching their values. So wherever there was a 0, 1, I make it a 1, 0. So that's how you fix them. And as soon as you fix them, you make all these violations go away. So you look at all these edges and you swap their values. How many changes did you make from f to f1? And it's precisely for every yellow edge that was there, you made 2 changes. You swapped their endpoints. So it's exactly equal to 2 times the number of violated edges across dimension 1. And by construction, after I finish this, there are no violations across dimension 1 for f1. But there is a worry. The worry is, does fixing violations across dimension 1 lead to more violations among other dimensions? So that's a worry, but let me at least impress that if this worry were not there, suppose this statement were like this swapping along or switching along dimension 1 did not lead to more violations along other dimensions, then I claim we are done, because I'll repeat the same procedure now on F1 across dimension 2 to get me to F2. The number of changes in F1 to F2 will be 2 times the number of violated edges in F1 across dimension 2. But since I don't have more, since F2, F1, this swap did not lead to more violations across dimension 2 for F, this number is at most 2 times the number of violated edges in F across dimension 2. And I have, after I go to F2, there will be no violations across dimension at most. So is this clear? If this worry were not there, then actually I can inductively proceed and get the whole proof to go through. So I want to sort of see if this part made sense. I can't see anybody, so.
It's good, yeah.
Okay. But this work, so we're back to this worry. So this is a thinking phase, I guess. And actually, it is a real worry. So before I get there, so let me explain what the worry is. So the worry is that I am across dimension 1. I want to fix this yellow edge. And when I fix this yellow edge and make it black, I'm worried that across some dimension 2, I've increased the number of violating edges. So the number of violating edges in F across dimension 2, across this vertical line was 1. It has become 2. That's the worry that I'm worried about. And indeed, it's a true worry if the range was not 0, 1. Okay, so here is an example to sort of showcase the worry. So here is a function on 4 points with these values. So clearly this is a violation, 3, 2. If I switch and fix it, so if I make this 3, 2, so 2, 3 into 3, 2, and this is not a violation, so this remains 2, 1, then indeed the horizontal edges become violations. Okay, so there was one violation before I switched across dimension 1, across the horizontal line. But after I switched and fixed the violations across the horizontal line, across the vertical line, I've made the number of violations grow from 1 to 2. So it is a worry. And indeed, that's why this paper only worked, this d by epsilon only worked for Boolean range functions. But as you know, it's a sort of, the nice thing is that this worry does not manifest itself with Boolean valued functions. And maybe the reason, again, sort of the similar cartoon picture, if you see, if I actually had Boolean values which got me to this kind of a picture where I had a violation here and a violation here, then I'm forced to have these values 1, 0, 0, 0. And if you swap them, then you, as in this case, you just work out and see that yes, this edge, which was not a violation, becomes a violation. But this edge, which was a violation, does not become a violation or sort of goes away. So the number of violations actually remains the same in this example. Okay. So the worry for for general ranges, sort of, at least in this example, by just looking at the value, goes away. And the proof is, well, there is not much more to say here. The proof is actually a case analysis of all these various possibilities that can exist. And in each possibility, we actually don't increase the number of violations.
So Deeparnab,
yes.
But for the proof, you need to consider only 2 dimensions at a time, right?
Exactly. That's why I can do this case analysis.
So there is a dimension in which the action is happening and the target dimension in which we are worried that something bad might happen. Only those 2 things need to be. And the pictures that you have drawn are reasonably representative of what is going to happen, right?
Absolutely. Yes. I just am not showing all the cases, but you can see there are some number of cases to be done. Maybe 3. But okay, so in some sense, it is still not a very illuminating proof. As in, it's a very local argument which says that this switching leads to, if you allow me to say, it sort of feels like an accident.
Yeah, and sorry for one more thing, but also you don't need to revisit a dimension that you have fixed.
I don't need to revisit.
And that is also, yes.
So maybe, so if I fix dimension 1 and now I'm fixing dimension 2, this same argument says, if when I fix dimension 2, it does not introduce more violations across dimension 1. But across dimension 1, there were 0 violations. So a function that was monotone across I don't introduce new violations across older dimensions that I've already fixed. Was that what you were just saying, Jack?
Yeah, yes, yes. I just wanted to, I was just
Absolutely.
understanding it aloud. Yeah, yeah.
Good. Yeah. So that's what the switching arguments is. So maybe what you
But
are.
I have a quick question. Can you hear me?
Sure, Mrinal.
So what you did here was you took a violated edge and you flipped the values. You could have done something else, right? You could have just made a 1 a 0 or a 0 or a 1. Like flipped at 1. You didn't do that. Was there for
No.
a reason?
Yes, because of this, that because I wanted this property that when I fix across some dimension, I don't increase the number of violations across any other dimension. So this is one way to do it.
I see. So it's not true for that that kind of a edit.
It's hard to sort of say that without knowing what exactly the edit is across.
Okay. Okay.
But there are, as in there's I'm no way saying that this is the only one that works. And in fact, there are other ways of,
Okay.
so you could fix across dimension 1 by looking at the more global picture, and that gives you a better argument. And actually, there was a follow-up paper which shaved off a factor 2 on this.
Okay. Okay. Thanks.
But this is a very clean argument, and it sort of works.
Thanks.
Excellent. So the sort of the upshot is that, so maybe I wanted to go back here. So it basically, this worry does not happen. And therefore, when I keep going from F1 to F2, the number of changes is bounded by the number of violated edges across F. And as Jaykumar was saying, that when I go from F1 to F2, I don't have violations across across dimension 2, but not across dimension 1, because the number of violated edges in F1 across dimension 1 is 0, and that number is also unchanged. So 0 remains 0. So both these things, so the same, this lack of this worry leads to both the properties that we needed, and the properties that we needed led to sort of this kind of a proof. So summarily, what this says, so the edge tester summary is basically this, that I sample an edge uniformly at random, I query the endpoints, I repeat it some d by epsilon times. If it is monotone, I'll always accept because I'll never catch a violation. And if it is far from monotone, then a simple analysis will show that I will reject with probability at least 2/3, depending on the big O that is in front of it. Okay, so it is 6:30. So can I take 10 more minutes, Akash? Is that okay?
Yeah, that's fine. That's fine.
Okay. So I want to sort of, so again, this is d by epsilon. So again, think of epsilon as constant. So this is taking number of queries is linear in D. And the lower bound that Fisher et al. Had proved is square root D. And so this was the question that people wanted to understand, whether the answer is square root D or D. So that, again, we know now that it's square root D, but let's sort of build towards that tester, which I'll tell you more details of more on Thursday. So before we go there, let's figure out that this edge tester, the d by epsilon is indeed tight. Okay. And the example is very simple. It's called this anti-dictator example. So I fix a dimension, and wherever that dimension was x, say dimension is I. So xi equal to 1, function value is 0, and xi equal to 0, the function value is 1. So this is the way the function looks like. And its distance is half, right? I need to make all these 1s into 0 or all these 0s into 1 to make it monotone. There is no way. So distance is half. And the violated edges, so the only violated edges are these, the blue ones, which have one endpoint, which straddle this dimension, this fixed dimension I. And so the number of violated edges is 2 to the d minus 1. And therefore, the edge tester would need to make roughly d queries to catch this. This is a good example to have in mind. And this example is good because it also tells us how to get better than D. So here's how you do it. So instead of looking at pairs which only differed in one coordinate, why don't we look at comparable pairs which differ in many coordinates? Because if we only focus on pairs that differ in only one coordinate and the function looks like this anti-dictator, unless it is precisely this coordinate, I'll never catch it. So that's the idea. And that leads to this sort of a path tester, which I'll formally describe next time. But you basically you want to look at pairs which are far away, and one way to think about it is you take a point X, and then you sort of walk up this directed hypercube a little bit to get Y. Basically, I take X and I look at a bunch of zeros and I make them coordinates 0 and make the coordinates 1 to get Y. And instead of querying, and I query fx and fy. So it's important that I'm only querying the endpoints and not all the points in the middle, because that will be too many things to query. So I query fx and fy. And if I get fx equal to 1 and fy equal to 0, then I got my violation. So I reject, otherwise I accept. So the question is, how long should we walk? And of course, if you look at this example, I should query the all zeros and the all 1 points, and that is going to prove to me that it is not monotone. So this is in the hypercube. So the number of the steps that you can walk, you cannot walk too much up the hypercube. It's capped by the square root of dimension, and that is sort of the reason for hardness in some sense. So what do I mean by that? So it's a hypercube. So we know that all the mass of the hypercube is really sitting in this middle layers. So if you look at all the points whose Hamming weight is d plus minus some c square root d, or c epsilon square root d, that contains 1 minus epsilon fraction of the mass. So in particular, you can take any function, and you can, the polar caps, as I call it. So the upper cap here, you make it all 1s, and the lower cap, you make it all 0s. I can always do that without changing the function too much. And so if the distance was epsilon far from monotone, such a function is going to be epsilon by 2 or 0.99 epsilon far from monotone by doing this change. What this change leads to is that if you take any pair where x lies here and y lies there, so x's Hamming weight is less than d by 2 minus c square root d, and y's Hamming weight is more than d by 2 plus c square root d, they're useless for us because I know their function values are going to be 0 or 1. Because this is 1 and this is 0. So they're useless. So you never want to sort of query points which are far away from this middle zone. And therefore, you don't really want to walk more than square root d. But you can walk square root d. And what I want to say is that in this anti-dictator with the polarized caps, in this kind of an example, square root d is the thing to do, and you'll catch the violation with probability 1 by root d. Okay. So again, I'm not drawing the caps here. I'm sampling an x. I walk up square root d steps to get y. I query fx and fy. What's the probability I start at the green zone and go to the blue zone? Well, the probability I start at the green zone is half. And the probability that I go to the blue zone is the following, that I'm taking square root d steps. And in each of the steps, if I cross this unknown dimension I, where the function is an anti-dictator, I will get into the blue zone. And once I'm in the blue zone, I'll stay in the blue zone. What is the chance of crossing at each step? Well, I have roughly half my values are 1. And in the remaining d by 2 zeros, one of them is the true coordinate that I want to flip. So there's roughly 1 by d or theta 1 by d chance of flipping the right bit at every coordinate. So that's this 1 by d. And I have root d such steps. So roughly the probability that this walk crosses from green to blue is roughly root d times 1 by d. Okay, so it's not completely kosher. You have to do some, but that's what you get. And that number equates to 1 by root d. So sort of, summarizing this, if my function was an unknown anti-dictator, unknown being no one tells me which is the dimension at which I have the violation, and also caps the things. So the top caps is 1 and bottom caps is 0. Then the following test, which samples a point, walks root d steps, and across these two things gives me, tries to find the violation. That test will succeed with probability 1 by root d. And so if you repeat this around roughly root d times, you will reject with probability at least a constant. So what I want to sort of say that the edge tester, which did make d by epsilon or order d queries in this anti-dictator, for this anti-dictator or capped anti-dictator, you can get away with this random walk tester or path tester or pair tester does make only square root d. And square root d, it cannot be better than square root d, because if you make more than square root d steps, this algorithm, you will get into uninteresting zones. So you cannot make more than square root d, so you cannot bump this probability up by more than 1 by square root. But, you know, this is only for the anti-dictator. So far from monotone functions don't look like this anti-dictator, capped anti-dictator. So how do you analyze this? So this sort of leads to this question, what do these functions which are far from monotone look like? What is our handle on this? So we need sort of structural insights on this question. And this is what this directed isoperimetric statements look like. So coming back to the slide that I had shown, this was basically saying that in the right, what we really showed in the GGLRS showed is that if you have a set which is far from monotone, or a function that is far from monotone, then the number of violating edges, or the out edge boundary, the directed out edge boundary, is large. And this should be compared with the undirected world, where it was already known long back that if you have a large enough balanced set, then the number of undirected edges going up and coming in, that is large. So this was the GGLRS was a directed analog of this Poincare kind of statement. Now it so happens that there is much more richer statements that can be proved for the undirected cube. Okay, and I'm flashing these statements, and I'm going to talk about them more in my Thursday lecture. What do these things mean? But at a high level, these capture that these, so in particular in this Margulis, this is the edge boundary, the number of edges, and gamma is like some sort of a vertex boundary. And this statement qualitatively says that the world either looks like there are lots of edges spread across lots of vertices, which is this is large and this is large. But if this is small, if the vertex boundary is small, then there are actually much more edges that are leaving that. So it's a much more nuanced statement than what just Poincare says. And what Talleyrand says, which is even more hard to understand just by looking at it, is a much more nuanced version of how these edges look like. So we're going to talk more about this on Thursday. And the testers for monotonicity actually all build on proving directed analogs of these isoperimetric theorems. So we proved this for Margulis back around 12 years ago, and Koch, Munzer, and Safra, which is this beautiful paper, proved the directed version of this. And this is what we will talk about. Actually, Seshadri will talk about this and the generalization of this to hypergrids and all. So these are the things that are coming up. So we need these structural properties to prove that the path tester works. And so this sort of, I'll end by saying what the agenda for Thursday would be. I'm going to talk about the path tester. So we'll recap, we'll talk about this path tester in a little more detail, but it's basically that, what we just said. But more, I'm going to talk about what these, like the previous slide, what these various isoperimetric statements mean, both in the undirected world and the directed world. I am not going to prove any of these isoperimetric statements. I will not have the time to do that. That Sesh will pick up on this when he talks about it. But what I do want to do is want to show how these isoperimetric statements, first explain what they are and how they actually let us prove that the path tester does take square root d. That square root d will work for any function. So that's my agenda for Thursday. So to summarize, we talked about monotonicity testing in general. I sort of showed you the state of the art for general posets. We talked about Boolean functions on the hypercube. We talked about the edge tester. And I sort of very quickly told you that there are connections to this isoperimetric theorems, which is basically saying if a function is far from monotone, what handle do we have on it to tell anything about our algorithms? So hopefully, this was the agenda for this. These 4 things are clear. So thank you for your attention. And I'm sorry that I went 10 minutes over time. And I'll be pleased to, address any questions that you have.
So thank you, Deeparnab, for the nice talk. So yeah, I mean, questions, anyone? Right. So I mean, I have one curiosity, Deeparnab. So for example, this strategy, the switching strategy that you showed for repairing a function that's far from monotone and that way to make this function monotone. Is there a good variation of switching strategy that you can use to think about non-Boolean functions, like functions with bigger ranges?
So you could ask for this same strategy for bigger ranges and it fails is what, or rather that proof fails. So what the old papers of Dodesh et al. Did is they actually did something called range reduction and then did so sort of piggyback onto this Boolean function. I'm putting a lot of things under the rug here.
I see.
I did not talk about this, and in hindsight, good that I did not prepare for this because I already went over time. But in some sense, the switching way of proving this edge tester bound is, it feels, at least to me, it feels like an accident that this works for the Boolean functions. There is a different way to prove the edge tester bound using the fact that there is a large matching.
I see.
And that proof is actually something that generalizes for real ranges. And this led to for the real ranges also, the best tester is D by epsilon. So that was not known till a different work of mine with Sesh, not this one, around the same time. And that so it's a different proof for the edge tester. And that proof, which basically says there has to be lots of violating edges, and that proof actually generalizes to real range in the correct way. So again, this is, you have to pick and choose what to show. And
Yeah.
but if you're interested, I can tell you what that method is. And I don't know if I still have not prepared the slides for Thursday, but I was thinking if I should show that at least on Thursday because it also leads to the Margulis statement.
I see.
But I'm thinking I won't have time in the 1 hour.
It's your playground. You're the judge. And,
Yeah.
I guess perhaps next time we would have a few more people. I guess my announcements perhaps did not go to as many people as I wanted to, but next time we perhaps would have more people. So, but thank you very much. If there are any other questions, please ask, guys. Otherwise, we can let Deeparnab off the hook. It's too early in the morning for him.
Well, it's not too early in the morning for me, but it might be too late in the afternoon for you all. So thank you again for the people who are there being here.
Okay. Yeah, then thank you very much, Deeparnab. Thanks for your time.
Okay, thank you, Akash. See you.
See you. Bye.
Bye.